Welcome back. In this lecture, we will continue the phase equilibria from thermodynamic volumetric data, that means thermodynamic property from volumetric data. But in particular, today we will look into the approaches to phase equilibria calculations. We will consider a very simple case. Okay, so to illustrate it, we will consider simple vapor liquid. That is VLE, okay, vapor liquid equilibria. Now, there could be many possibilities. In order to simplify it, we will consider 4 cases. So, let me just write down the 4 cases. Usually, it comes in these 4 variables or 4 different varieties. Okay, so there could be 4 different varieties of phase equilibria kind of calculations. So, and what it depends on what kind of data which we have. Okay, sometimes you may have only the liquid compositions, sometimes you may have only the vapor compositions, sometimes you have temperature but not pressure information, sometimes pressure but not temperature information, and so forth. So, let me just write down. And so, one first could be, let us say, given temperature and liquid composition, calculate pressure and vapor composition. What kind of a point it is? Like, calculation is called what? Bubble point, because the bubble of vapor. So, you are basically calculating the composition, which means when this vapor forms, right. So, this kind of calculations are called bubble point for known T. Okay, temperature is known, right. Okay. Now, let us continue for another case where given pressure and liquid composition, calculate temperature and composition. So, this is again bubble point, but known P. Okay. All right. So, now these are the 2 possibilities. The other possibility is when the composition of the vapor phase are given and you have been asked to calculate the composition of the liquid phase. In such case, that will be dew point, because when the first drop of liquid forms. Okay, but depending on what conditions available, it could be known temperature or known pressure. So, I am going to just write down that. Calculate P Tx. So, this is dew point, known T, and this is dew point, known pressure. Okay, so these are the simple mechanism. Now, the question is, how do you calculate when you have any one of the situation? Okay, so you know the number of variables, you know the constraints. So, let us now write down and see how we can approach or develop this methodology to solve such a problem. So, considering that it is a mixture, okay, still it is a vapor liquid system, but it is a mixture, and so for M component mixture, for M component mixture, how many parameters we have to find? We have M component mixture, how many parameters we need to evaluate? For in any of this, unknowns are M minus 2. So, but the temperature, so unknowns are pressure and the composition, right. So, in general you have to evaluate m plus 1 parameter. Okay, some may be dependent because y's are m and p is 1. So, m plus 1 parameter need to be evaluated. Which are nothing but p, let us say in one of the case, for the case of 1, for case 1 we have p y1 ym. Okay. So, these are the number of variables. So, let me just write down the number of constraints also in this. So, what are the number of constraints? Now, we say that m is basically the number degree of freedom, that is what we are saying it, right. So, let me also put it, so here m plus 1 constraints are there. Why is that? See, remember how we have evaluated or determined the Gibbs phase rule? We made use of equilibrium condition. Now, in this case, the number of constraints are basically the equality. Temperatures are going to be constant, we do not have to bother about temperature. Pressure, we do not have to bother about it. We can simply use chemical potential or the fugacity. So, let me write down there are m components, that means the m equations for fugacity. So, F I L, temperature, pressure and composition. Okay. This should be F I vapor, again temperature, pressure and okay, where I is equal to 1 to m. So, there are m equations for each of them. In addition, since y's are connected, we have yi is equal to 1. So, these are how many constraints? M plus 1 constraints. Okay. Now, similarly for dew point calculation, so this is for bubble point calculation. For dew point calculation, okay, that means case 3 and 4. The m plus or m plus 1 constraint is summation xi is equal to 1, right. Okay. Now, this equation, so let me write down the equations in so that I can make use of it later. So, this equation, let us say is 1, this is 2. So, equation 1 and 2, if you look at it together, basically equation 1, these are applicable when the fugacity is known as a function of temperature and pressure, isn't it, and composition. F is known as a function of T, P and X, okay, or composition X or Y. Okay. When we have also seen that the fugacity can be also related in terms of the molar volume. So, when the information is available not in terms of just pressure, but in terms of let us say molar volume, then we can write the same expression as FIL is equal to FIT VL, okay, composition FIT V vapor Y, okay, this is right. For I is equal to 1 to m, okay. So, this is useful when F is known as T, V and composition, okay. Then this is more convenient to write it, and in such case when we write it, we also write the pressure also, because pressure in the both the phases, particularly in the pressure along this scalar version of it, is temperature VL X should be same as Okay. So, remember pressure is basically tensorial component variable. So, the trace of it, okay, or the diagonal average value of the diagonal version is basically going to would be hydrostatic pressure, okay, or that is the pressure which is felt by the single phase, but at the interface only the normal component of the interface will be at equilibrium based on the force balance. But overall the pressure felt by the vapor should be same as this. So, this is a condition, assuming that of course there is no gravity effect. So, this is something which we consider.
Pressure should be equivalent to equation.
See, we what we say is the following, because the pressure which you are talking about is basically the scalar version of it. So, okay, mechanically the pressure only at the interface will be fixed, okay, but this same pressure, this is the same pressure here in the your phase here will be same in the rest of the component, okay. The normal pressure will be same as within the phase. In other words, if this question is very interesting. So, if you look at two phases here, okay, you have alpha and beta. So, this component is going to be same, right, and this component tangential pressure will be little varying in order to have interfacial tension. But we are talking about this pressure here only, okay, that this will be the one. But the reason is that this pressure, when you go away from the interface across here, all this pressure will be same, isn't it? So, that means if I plot a pressure profile, the normal pressure will be like this across the interface. If I plot it, pressure as a function of distance, and we are taking a distance like this, okay, the normal pressure will be this for all of it, okay. Whereas the tangential pressure, the one which is the other component of the pressure, will be something like this, need not be exactly in this form, but I am going to try that. So, something like this, there will be deviation, it has to be a mirror image, something like this, okay. So, this is the region which will be in this is the region, okay, which basically is the interfacial region, right. And because of these changes in the normal pressure and tangential pressure, the surface tension gets out of it, in the sense there is this contributes to the surface tension rise. But otherwise in the bulk region, that means somewhere here, so this is, let us say, interfacial region, then this bulk region, the normal pressure and tangential pressure are the same. In these conditions this holds, okay, this pressure will be equal, okay. Okay, so since we have addressed that question, now let me also consider the other thing. So, pressure will be written as this. Now, depending on whether it is a bubble point calculation or dew point calculation, you are going to write it like this. This is going to be bubble point. You are calculating the bubble point, which essentially means you do not know the vapor phase composition, okay. And similarly, this is dew point, okay. So, in this case, if you notice, you have a fugacity for known values of T and V and composition, but the number of variables have increased for such a case. If you write this, the number of variables are, is it m plus 1 or is it more? It is m plus 2, because you have volume also which we need to find out. You do not know the volume, you do not know the pressure, and of course the composition of the relevant phase, whether it is a bubble point or dew point calculation. So, the number of variables are now m plus 2, and number of constraints have also increased, because we have added this one additional term of pressure. That means number of constraint is also m plus 2. So, you can solve this such a problem. Okay, so this would be VL, VB and composition. Okay. Now, this is your, let me write down the equation numbers. So, this is, let us say, 3 3, 4, okay, and this is your 5. So now if you use this 3 to 5 equation, okay, along with fugacity expressions, okay, based on earlier which we have discussed equation of state, because that was discussed last in the last lecture, then you can try to solve these expressions. Okay. So this will give us m plus 1 non-linear equation and one linear equation. Okay. You can drop this also. You can make use of this and represent. Let us say, if for the case of summation yi equal to 1, you can write simply ym is equal to 1 minus yi minus 1. So with this expression, if you plug in there, you get m plus 1 equation with m plus 1 unknowns. Okay. But these are all non-linear equation. So assuming that the equation of state which we are trying to do, make use of it, is basically cubic. If equation of state is cubic, then we actually can write this expression which we have written here in terms of the earlier expression, this. Okay. So how we can do that? Let me just write down this, because at the end what we are trying to do is we are trying to calculate the fugacity as a function of temperature, pressure and composition. So given the data available is basically in the volumetric form, and the molar volumes of fugacity dependence on molar volume is known, which if not in from the experiment, we can make use of equation of state, and then we can try to use it, solve it in order to obtain the fugacity in terms of temperature and pressure and composition. So how do we do that? To calculate F and Fv, temperature, pressure V, we proceed as follows. Okay, for case of liquid Tpx, since we have to evaluate this, I am going to write down the algorithm, a simple algorithm, how we are going to do that. Given Tpx, calculate the equation of state variables, which is usually a and b, if it is equation, if it is a cubic equation. So these are parameters of equation of state. Okay. Then solve cubic equation of state for 3 volumes, right. You are going to get 3 volumes, okay, and you have to find out, let us say, let me just write down V1, V2, V3. Now for the case of liquid, you take VL as the minimum value of this. Okay. Right. So in such case, you can write FL Tpx is equal to Fi Tv x. Okay. So what we have done is basically we have made use of an equation of state, could be van der Waals equation of state, could be other equation of state. Solve, these are cubic equations of state, solve it, we obtain 3 values of V's, take the molar volume of liquid which corresponds to the minimum value of it. Okay. So that is to get FL Tpx. Now what about FV Tpy? So this is again we can think of that, okay, we can write down the algorithm. Given Tpy, calculate again AB, okay, that is parameter for equation of state, solve equation of state leading to 3 values, then right, we are going to take the molar volume of vapor as maximum value among these 3, and thus we get FLV TPY as FL okay.
So why are you taking minimum or maximum?
Yeah, it's a good question, because since for the vapor liquid equilibrium you have a vapor which is going to be maximum, having the molar volume much more than the liquid, and since you are using the equation of state for a given temperature and pressure, okay, you are going to get different values. So, the least value, stable values, okay, positive value will be for corresponding to the liquid, and the maximum largest positive value would be corresponding to the vapor. This comes directly from the equation of state, the way the equation of state diagrams are. So, we are making use of that and understanding from that point of view that this would be separated largely by much bigger differences, and since there is only one possible value, so you will see that the roots are going to be having some imaginary values also. You have to ignore that, you have to take only the real values. So, let me just make a concluding remark as far as equation of state approach is concerned. So, this is equation of state approach. Okay. Now, the advantage is that you can readily adapt or make use of any, or you can use this approach for any fluid, okay, having an equation of state. So, that means readily adapted to any fluid phase equilibria. Okay, phase equilibria problem. So, this is one of the advantage. You can find out even the critical lines for the mixture using this approach. What are the problems related to equation of state? Because of the non-linearity of this set of equations, the way you solve could lead to unstable situations also. Okay, so numerically it become unstable. So, thus finding such a solution, making use of equation of state could be a problem. In addition, since equation of states are, for many systems are not well developed, then it has a limitations with respect to the quality of equation of state which you are using for a given system. Thus, it limits the way or the use of it. So, this is the disadvantage. So, the algorithms can be unstable, right, and may be costly to implement. So, algorithms can lead to instability, costly to implement, which means it may take time to finish the job, right. And we have a problem of equation of state, okay, issues with equation of state. Okay. So, this is not the best approach to solve vapor liquid equilibria for mixtures. There are other methodologies such as phi gamma approach, which I am going to take in the next lecture. Okay. So, see you in the next lecture.